My name is Csanádi. I'm from the Institute of Slovak Academy of Sciences, as all the others. I was a PhD student. I started that kind of work during my PhD studies, and of course later on we extended this work from carbides, borides, nitrides to these high entropy counterparts of them. So now I'm a postdoc, and I would like to talk about the deformation and fracture of high entropy carbide grains, because basically we are testing only the grains, because it's very difficult to test all those materials. I mean, all the parts, grain boundaries, other things. So we just basically focus on only the deformability of the grains using such state-of-art techniques like micro and nanomechanical testing techniques like indentation or pillar compression. So I almost forgot to mention that the work which I'm going to talk about, it's a common collaboration between Slovakia, Hungary, and the United Kingdom. So basically, the materials were synthesized in the United Kingdom, and characterization testing was done here in our institute, and also partially some of the measurements, including EBSD, was done in Hungary. So the topic, or I mean the presentation is about basically some introduction, a little bit of aims. I will list the experimental techniques, and also I will show you the results about the structure and the deformability of high entropy carbides. And basically I will sum up this at the end. So the story begins where we're looking for some materials which can survive very extreme conditions. It means over 2000 centigrades in oxidative atmospheres, we really need specific materials which can survive that harsh environment. And these environments usually needed for propulsion systems, as you can see, or leading edges in space vehicles during re-entry to Earth. So not too many materials are good for that purpose, and just only a few very limited group of materials are good for that purpose. Of course, if we check the available so-called ultra-high temperature ceramic materials, we can have a list. But unfortunately, not all of them are good for that extreme environment. This is because many of them can burn. So, for example, graphite is the highest, the material which possesses the highest melting temperature, but it burns over 900 centigrades. Also, in some cases, there is some problems with the heat transfer. So the materials, what we really look for as an ultra-high temperature ceramic material, should possess good thermal conductivity and relatively low thermal expansion. So this means, for example, oxides immediately pulled out from this list. And basically what remains is about 20 materials. Those are basically the borides, carbides, and nitrides of group 4 and group 5 transition metals, because those are the materials which has the highest melting temperature of the materials known. These carbides, borides, nitrides has not only high melting temperature, which makes possible to apply them for this apply them as a ultra high temperature material, but they also have high hardness and high strength. At the same time, they have excellent oxidation resistance and good thermal shock resistance, which is necessary during, for example, re-entry of space vehicles to Earth, because they need to somehow take away the heat from those edges. So the thing is that we have a limited group of materials, and of course we can mix them, we can make compounds or composites from them, but they are still limited. So we were looking for some materials which can extend that limited group of materials, and the motivation came from high entropy alloys. Those materials are well known from 2004, and the concept how high entropy alloys are formed was basically the motivation of the development of high entropy oxides, which were first published or produced and published in 2015. Up to that time, no one knew that is it simply possible, because it was thought that probably high entropy ceramic materials could not be formed in a stable single phase form. But in 2015, it was shown that it exists and can have some interesting properties. So based on the success of processing ultra high temperature oxides in high entropy oxides, as let's say the counterpart of high entropy alloys, additional studies appeared on the ground. So transitional metal borides were synthesized in 2016, and after 2 years we developed, I mean, the English partners who we work with, they developed the transition metal carbides, and we had to have a chance to do some testing, characterization, and develop even more the materials. So this was in 2018. It's a very, very fresh, a new group of materials. And since that time, many, many publications appeared in this field, more than 100 papers published about their synthesizability, characterization. But to understand how they behave, we really need to know the mechanical behavior and the connection between structure and mechanical properties. And this is what is still missing, and this is what we are working on in our institute. So, sorry, okay. So the aim is to study the structure of one specific high entropy carbide, this hafnium, tantalum, zirconium, niobium carbide, using macro and micro testing, investigation of the deformability of these materials, and finally understand the relation between the structure and the deformability. The experimental techniques, what we used first was the synthesis of this kind of material. As I mentioned in the beginning, that high entropy carbide material was synthesized by our English partner in London, and using a two-step spark plasma sintering technique. And at the same time, there were also base monocarbides were synthesized. So hafnium carbide, tantalum carbide, niobium, and zirconium carbide, just as a comparison of the mechanical properties, what we investigated later on. After the synthesizing the samples, we did structural analysis using XRD and STM. We did scanning electron microscope to check the surface, to select some specific areas for the testing, and also at the same time we did structural analysis, chemical analysis at micro level and also at nano level. To know the orientation, we performed EBSD, It's a so-called electron backscatter diffraction scattering to determine the crystallographic orientation of the grains. And as you can see on the left side, we have a cubic structure. So maybe I forgot to mention that that kind of high entropy carbide possess the same crystal structure what the original base monocarbide had. It is a cubic phase, cubic symmetry, and as you can see on the right hand side, there are different grains with different orientations, and from those maps we selected specific crystallographic orientations from which we prepared different micro rigs. For example, we prepared micro cantilevers. As you can see on the left side, we selected grains because we were focusing on only the mechanical behavior of the grains. So we selected large grains from which we fabricated the cantilevers. I mean, cantilevers from the top was entirely in the grain. Unfortunately, in the bottom, I mean, in depth, we were some cases problems because we never knew how deep was the grain what we selected for the fabrication. But of course, those tests, which turned out that contained several grains, not only one, were excluded from the data analysis. So all in all, we fabricated 7 cantilevers from 2 different crystallographic orientation from the top using focus ion beam technique. Regardless of the top orientation, the fixing was always parallel with the 001 direction. So that kind of cantilevers were intentionally fabricated such that to be parallel to the surface of 001. This 001 has the lowest fracture energy based on some DFT calculations. So that was the reason why we selected this specific orientation. As you can see on the right side, here is how it looks, the S-fabricated cantilever, which was used for testing. Additionally, we prepared also different kind of structure, not a pillar, not a cantilever, but a micropillar, as you can see on the left side. So here we also selected specific grains from which we fabricated micropillars. Those grains which were selected for the testing were intentionally selected such that their orientation was not the 001, but a slight shift from 001 towards the 111 direction with a degree of about 14 degrees. The reason why we selected that specific strange orientation, I will explain later. So from this grain, or that kind of grains, we prepared 4 micropillars, not only in the high entropy carbide material, but also in the monocarbides, because we wanted to compare the deformability of that newly synthesized material with the base monocarbides, just to be able to see what is the difference compared to them. The S-fabricated pillars are shown here with a size of 2.5 micron in diameter and 5 micron in height. And that pillars were used for compression. We used the nano indentation machine equipped with a diamond flat punch tip used for compression using a constant load rate at room temperature. Additionally, we did also nano indentation. As you can see, it was basically a very shallow nano indentation using a maximum depth of 300 nanometers using a Berkovich tip. And as I mentioned at the beginning, as we fabricated microcantilevers, those microcantilevers were fabricated with the aim to compress them using a sphere and conical tip and record the fracture properties. And finally, all the fractured or compressed or deformed materials were observed, examined by SEM. So what we got, first of all, the results of XRD showed that the ball milled powder, the mixture, I mean the niobium, tantalum, hafnium, zirconium carbide mixture, contained all the peaks, which means that during ball milling, basically there were just a mixing, but because it was a relatively low speed milling, not a mechanochemistry, the original phases were detected. So it means the powders were mixed, but there was no basic chemical reaction between them. After SPS, so after sintering, you can see that the peaks disappeared, so which confirms that a single phase bulk material was formed. In that graph, you can see a slight peak which corresponds to an oxide peak, but this is just because this graph is a relatively old graph, and this was one of the first trials. So since that time, we prepared also other type of high entropy carbides, which was completely single phase without any oxides, remaining oxides. And the peaks, as you can see, falls between the individual peaks. So in the right side, you can see those lines, but those lines are really lines. This is just for visualization purpose, where the individual monocarbide peaks should be present, but they are not there. We can see only one peak, which corresponds to this structure, this hafnium, tantalum, zirconium, niobium carbide. So this confirmed that it was possible to synthesize a single phase material, and the single phase material showed real atomic randomness at different levels. So at nanoatomic level, you can see that the individual atoms are distributed randomly. And of course, also at micro level, when we observe several grains, we could say the same. So it means we got something which can be shown on this scheme, that we started from transition metal carbides, which has a cubic structure. It's a sodium chloride structure, where the metal elements can be hafnium, tantalum, zirconium, niobium, vanadium, titanium. Those are the group 4 and group 5 transition metals. But once we mix them and subject to SPS, due to the diffusion, metallic elements are replaced by each other randomly, as it was confirmed previously by EDS and STM analysis, forming a structure which looks like similar to shown on the right side, where we can see randomly distributed transition metal elements in this sodium chloride structure, which somehow generates a lattice distortion. This lattice distortion is due to the fact that we have different transition metal elements with different atomic size, different valence electron concentration. So this distorts a little bit the lattice. This is an exaggeration of that lattice distortion, but I wanted to emphasize that this is real, and this can be also measured, and already it has been confirmed by different techniques that lattice distortion exists. It means that basically similar to that. And this lattice distortion should cause some lattice or strength enhancement or hardness enhancement due to this distortion, which makes difficult to this location to move forward. So to prove it, that this is the case, we did basic nanoindentation, and we compared the results with monocarbides. And as you can see, on the left side, you can see only 2 monocarbides, tantalum and hafnium, but this is only my fault because I forgot to insert additional graphs we have. But believe me, The reason why I did it, just to make confusion, to avoid the confusion, hafnium carbide is the hardest of the four monocarbides, and tantalum carbide is the softest. So the rest of the two, the niobium and zirconium carbide, should lie between them. And what is interesting, what we could see, that even the binary carbide, which contains hafnium tantalum carbide, has higher hardness, but this four elements high entropy carbide has even higher hardness, which fits to the theory what we thought at the beginning about the lattice distortion. Of course, many questions remains. For example, what is the case in a deformation when it's not multi-axial, like in case of indentation, but let's say a simple compression? Do they behave brittle or ductile? Or anyway, what kind of slip should we expect? So to answer for these questions, and basically what is the fundamental deformation mechanism behind those things, we have to do additional testing and characterization. For that purpose, we did micropillar compression, as I mentioned in the beginning. So we selected grains with a specific orientation, which I will explain you later, and we compressed them. We compressed first the hafnium carbide samples, as you can see in green. They deformed to a specific level and then they broke. You can see also fractures. So you can notice on the top there are some lines, it's basically fractured surface due to some dislocation activity. Maybe if you have good eyes, you can see on the right side image some ellipsoidal lines. Those are slip patterns on the surface. It's very hard to observe it on hafnium carbide before the final failure occurs. But if we check tantalum carbide, which was able to deform much more farther, so it means the deformability of tantalum carbide was a little bit better than hafnium carbide, we could see much better the slip lines on the side. Okay, one can argue that we have also pores, and this could have influence on deformability. Those who are saying this have completely right. Yes, pores significantly influence the deformability, but not in case of pillar compression. In case of pillar compression, if those pores are located somewhere inside or at the bottom of the pillar, it has some influence, of course, but not as significant like in case of micropillar, not like in case of cantilever bending. So as you can see, there are many slip lines on the surface. We can see cracks, also top, also on the side, but the pillars are still in one piece. So it means tantalum carbide can deform more than hafnium carbide based on our experience on micropillar compression. Considering the last one, which was the most important, it's the high entropy carbide indicated in blue. What we can see first, it has a significantly enhanced yield point. Instead of 4 or 3, it's 6 or even more. Regarding the deformability, it's at least as good as hafnium carbide or similar to tantalum carbide. So it means that there is something which can deform, at least at that specific orientation what we selected, similar to tantalum carbide, but has enhanced hardness or strength. Showing the results of microbending, it's slightly different. We found some cases when we could see, or we can reach stresses about 12 GPa. It was basically linear. So basically we didn't see anything interesting, almost linear behavior, and then a fracture. Those curves correspond to those cantilevers which fractured at the fixing. So as you can see here, indicated by this red mark. Those which has lower strength corresponds to those cantilevers which failed on some defects, as I mentioned earlier, which defects were located somewhere farther from the fixing and therefore fractured a little bit earlier because they act as a stress raiser and increase the stress, and therefore the cantilever failed. So what we got basically two groups. There was one group which was no visible fracture origin, those which failed at the beginning, I mean at the fixing of the sample of the cantilevers. Here we can see that the strengths were quite similar. They were basically 12 GPa, which is quite high. We hardly see any fracture origin, and what we see, there is a slight yielding, about 9 GPa but they are basically linear, and only a slight plasticity or slight deviation from linearity before the final failure occurs. The fracture origin turned out to be connected some defects which is on the side, those most probably thought to be some FIB-induced defects, and because the stresses are the highest at the fixing, and because defects are on the side, they usually started some crack initiation and fracture, and this caused this kind of Haeckel regions in all cases what we observed. The surface, what we see, is quite smooth, and those surfaces are the 001. So the cleavage plane, as we expected, was the 001 plane. Of course, at the bottom part of the cantilevers, there are some deviation, but this is simply connected to the change in the deformability once the fracture starts to propagate, because in that case, stress field completely changes. And at the same time, on the top side, we have always tensile stresses, while on the bottom side we have compressive stresses, and this cause different kind of failure. In case of defected cantilevers, we see everywhere that the fractures originated from the defects, not exactly from the pores, but most probably connected with cracks formed around the pores, and those cracks propagated and resulted a final failure of those cantilevers. And of course, depending on the location, the size of those pores and cracks, initial cracks, the strength varies between 4 and 9 GPa, and because they are present and fails immediately when it reached the specific value of fracture strength, there was no yielding observed. Here we can see the fracture origin. It's connected to a nanosize pore, and most probably close to the nanosize pore there should be some crack as well, but due to the high resolution we were not able to resolve that. So basically what we got is we were able to synthesize a new type of material. It was in a form of a polycrystalline single-phase material, so-called high-entropy carbide material, which has enhanced hardness, also strength, improved ductility, at least compared to the monocarbide, I mean the most brittle monocarbide, and at the same time we are able to broaden the limited set of ultra-high temperature ceramics, which was the basic motivation of our work. Because if you consider only the 6 group 4 and group 5 transition metals, we have 6, let's say, carbides, as I listed earlier: titanium, vanadium carbide, zirconium carbide, and the others. So we have 6 options to form high ultra-high temperature carbides. But if we select 4-element carbides, for example, the material that we just showed before, we have 15 options how to select the 4. So instead of 4 monocarbides, we have now 15 4-metal element high entropy carbides, which can be synthesized. So it gives a vast new compositional space for forming or synthesizing new materials, new ultra-high temperature ceramics materials. Of course, there is a other side of this, that we never know which kind of composition will be stable or have even better properties than the monocarbides have. So there is recently strong progress in the direction to be able to predict their properties, at least regarding the stability. Because if we select not 6 but select additional more transition metals, we have combinatorial explosion of these possibilities. So it's basically, it's a very new field, but many possibilities are possible. So the question is, of course, still remains: what is the structure property relation between at least regarding that material, specific material that we tested? So what we can say, first we have to start at some basic levels. So group 4 transition metals, it means zirconium and hafnium carbide in our case, they are basically brittle. I mean, indentation techniques revealed, also TEM work revealed, that they have a dominant slip system of the so-called diagonal plane, so this 110 plane with a slip direction of 110. In case of group 5 transition metal carbides, which comprises niobium and tantalum carbide in our case, can deform in a ductile form, where the slip plane is the 111 instead of the 110. The slip direction exactly the same. This is due to the fact that group 5 transition metal carbides have extra valence electron, and this makes a bit more metallic character to them. Theoretical studies showed that the critical reservoir of shear stress for that kind of slip, I mean, which is on the left side, so the 110 plane, lower compared to that which is the 111. In the literature, we can see additional information that there are other studies who said that they are equal. So we didn't know what is the case, especially not in for high entropy carbides, which have never been synthesized before. So we simply wanted to test this. And in order to test this, we calculated the Schmidt factor for different slip planes, not only the 111 and the 110 what I showed you before, but also the 100 type. And so this right side image shows the orientation dependence. So I mean, if we tilt a cube from the 001 direction to the 110 direction, so from the through the corner, we can see the transition of the Schmidt factors, how it changes with the orientation. And we were interested to select a specific crystallographic orientation where the Schmidt factor has no influence on the deformability. So therefore, we can test immediately which one has the lowest critical reservoir shear stress, because the orientation does not take place. And this orientation was found to be at 14 degrees. So that was the original reason why we selected specific grains with 14 degrees to test whether the first so the brittle, or the second, the more ductile slip system is the dominant one. So now we had to just check what we got, and we carefully observed the slip patterns on the side and also the top. From the top side and also from EBSD, we knew immediately how the pillar was oriented. As you can see, we can see some cracks parallel with the edges of the cube. And if we assume that we have the 110 plane activation, we should get this slip pattern which look like that. I mean, the top of that plane should be perpendicular to the edge. If we have 111 type slip plane activation, we have similar slip pattern. I mean, the side, the pattern looks similar. However, the top of it should be at the corner. So we didn't do anything special. We just simply checked what is the case in our tests, and we got that this is the first, the 110. We were very surprised, but that's the fact. So in all cases, not just for the ultra-high temperature or for the high entropy carbides, but also for the monocarbides, it was unique that the 110 was activated. So it means we could confirm that 110 has lower critical reserve shear stress compared to 111. So here is the fact what we got. So in case of micropillar compression, 110 we found to be lower than the 111 type. However, in case of indentation from the literature, we got a little bit different results, because as I just mentioned before, the 110 was known for group 4 transition metals, but group 4 transition metals, the 111 was the dominant one. So to explain this, we had to check additional things, which is the presence of the partial dislocations. So it means that there is a case when partial dislocations can be formed, which makes possible to the activation of the 111 plane. And this partial dislocation form strongly depends on the testing orientation. So that is the key which explains why we got different compared to macro testing or monocarbides. So in case of indentation, which is a multi-axial stress field, so basically anything can happen, it means that there is a possibility to activation of partial dislocations if the material willing to that, which is the case for group 5 transition metals. However, in case of micropillar compression, because we had specific crystallographic orientation, we were not able to activate those partials, even though they should be activated during indentation. So that's the case why we got 110, not 111, for example, for tantalum carbide. So basically, what we got is that we have, so the structure deformation relation up to our best knowledge is we have group 4 transition metal carbides. In our case, it was only zirconium carbide and hafnium carbide. Of course, titanium carbide is also in this list. They are relatively bigger atomic size compared to group 5. And they have valence electron concentration of 8 because they are in group 4. And for those materials, there's no chance to dissociate to specific partials at room temperature. This is confirmed by, or this is predicted by DFT calculations. And this is the reason why they slip only on the 110 planes, and which is the so-called brittle plane. Of course, if we increase the temperature about 800 degrees C or even more, there is a chance from brittle to ductile transition, but we were interested only in room temperature because this is the problem usually when we have brittle materials. In case of group 5 transition metals, which comprises niobium carbide, tantalum carbide, and also vanadium carbide, which is not indicated here because we did not deal with that. They have an extra electron on their outer shields, and therefore they have more metallic character, which I try to indicate on the right side. And this metallic character makes possible the dissociation of dislocations into partials on the 111 plane. And therefore 111 plane can be activated even though the original activation, so the critical reserve shear stress for this specific slip system, is higher than that one. In case of high entropy carbides, specifically that material, that hafnium, tantalum, zirconium, niobium carbide, we have the mixture of them. So we have different atomic size of the transition metals from which it builds up. We have local variation of the valence electron concentration, and this kind of mixture causes lattice distortion. And this lattice distortion acts as a barrier for the movement of dislocation, so we expect enhanced hardness and strength, and this is the case what we experimentally verified. However, at the same time, we have an effective valence electron concentration due to the equal portion of group 4 and group 5 transition metals which took part to build in the structure. So we have 8.5 effective valence electron concentration, which is slightly higher than the 8 which has for group 4 transition metals. So it means that we have a slightly increased metallic character for compared to the zirconium carbide and hafnium carbide monocarbides, which means that we have, or we can expect, improved ductility, and this is also the case what we could prove. So this is something which is completely new, and at the same time is very interesting, that even though we're just not able to synthesize new materials using this technique, which is well known for metals as a so-called high entropy alloys, so we are just not able to synthesize new materials or thousands of millions of materials, but we can expect at the same time enhanced strength and also improved ductility, at least compared to the base brittle carbides. So to sum up what we did, we synthesized polycrystalline single phase high entropy carbides, which broadens the limit of broadens the limited set of UHDCs. We got enhanced hardness and strength using different kind of techniques. In micropillar compression, we found plasticity, or not only for hafnium tantalum carbide, but also for high entropy carbide. Slip activation confirmed that the 110 type slip systems has the lowest critical reserve shear stress. Schmidt factor calculation revealed that that kind of slips, the 111 type slip system can be activated by partials, but this is only connected with specific crystallographic orientation. So in case of indentation, it's possible, but in case of micropillar compression, may not be possible. And the structure analysis, the structure deformation behavior analysis revealed that valence electron concentrations play a significant role in their deformability, and this makes or may make stronger hex compared to zirconium or hafnium carbides, and more ductile at the same time. So thank you for your kind attention.